So I've been talking a lot about how if we have a solid and we heat it up, or we have any sort of collection of molecules and we heat it up, it expands. And I've talked about why. That's because of the internal energy causing them to move further apart and become less tightly packed. This is a solid here. And I've also mentioned that the volume increases and that affects density. So the cooler object has a smaller volume, and the larger, hotter object has a larger volume. So I've already talked about temperature and volume and how they affect each other to some degree. But there is one more sort of property that is affected when we talk about gases, and that is pressure. Now, we're all familiar with pressure to some degree. However, some people don't quite understand it, and I'm just going to quickly explain what pressure is. So let's say I have a balloon, and I put air into it. Now we know when you put enough air into a balloon, it expands, it becomes this round shape. Why does it do that? Well, inside the balloon, we have inserted air particles, more air particles than are outside. And so what air particles like to do is that they like to move around a lot. And eventually, there's going to be some air particles that hit the wall, like this, and then bounce off it. When they hit the wall, they cause it to indent slightly, just like you would imagine. And this happens millions of hundreds of times with thousands upon thousands of little particles all along the surface of the ball. Now, inside we have more particles than there are outside, which means the collision on the inside is going to increase. So there's going to be more collisions from the inside, which push it out. And that's why the balloon expands, and that is the essence of pressure. Essentially, pressure is molecules hitting the wall of a container. That sort of defines pressure, internal pressure anyways. So let's construct a system that's going to allow us to test this. So let's say we have a box with a pressure sensor on all of these walls and a piston that can move up and down with another pressure sensor on it. So we can tell the pressure and we can move this this piston up and down to change the volume, and we can also affect the temperature inside this. And we fill it with air, and there's no way for anything else to get in or to get out. That amount of air is set. So let's see what happens if we start moving this piston up and down. So we move it up. What happens? Well, now there is empty space. And so these guys, they move up. Their energy takes them and they fill up the empty space. But since there is a set number of molecules, that means that it's sort of thinned out a bit. There are less molecule per section, so per square centimeter now as a result. And so that means that the parts of the walls being hit, that has actually decreased because there's less air molecules to hit all of the wall. And so what we see is that volume is inversely proportional to pressure. Volume is inversely proportional to pressure, and that is our first law, which is Boyle's law. Boyle's law. Volume is inversely proportional to pressure. Well, okay, we've got that. Now let's reset this structure, and now let's unlock the piston. Unlock the piston so that it's free to move up and down, but we don't move it. We have the same number of molecules inside this box, and instead we increase the temperature. Well, that's going to increase the energy in here, so they're going to be bumping around a bit. And what that will do is cause them to expand, and that will push this piston upwards. And so we see, okay, now there is more volume in here. So the volume has increased. And so, okay, we can see that temperature is directly proportional to volume, because as temperature increases, the volume increases. And so that is Charles's law. That when temperature increases, the volume increases. So now let's lock up this piston. So now this piston can no longer move. We're not going to let it move. And then we're going to increase the temperature and see what happens. Well, now they're all energized again. They've all got that internal kinetic energy from the heat, and they're bumping around, but they don't have anywhere to go, and so they end up hitting the walls more often, and so pressure increases. And so that there is the pressure law. That pressure and temperature are directly proportional. So temperature is directly proportional to pressure. And these are our three laws. And you can see that each law has one of these three that they're independent of. So for example, Boyle's law is independent of temperature. So this is independent of temperature. Charles's law is independent of pressure, and the pressure law is independent of volume. So they're all independent of one another. So what we're going to do is we're going to take these three laws. Let's start with Boyle's law, that pressure is inversely proportional to volume. We're going to take this and we're going to translate it into an equation. So we can say, okay, the P, the pressure at the start, and the volume at the start, if we multiply them together, that is going to equal the pressure at the end, so P2, multiplied by the volume at the end. So these numbers are going to be the same. Now let's look at Charles's law. Okay, temperature is directly proportional to volume. Okay, so that means that if we take the temperature at the start and we divide that by the volume at the start, that's going to be the same as the temperature at the end divided by the volume at the end, or vice versa. And then if we do the pressure law, so pressure is directly proportional to temperature, we see, okay, P1 over T1 is equal to P2 over T2. And there are some patterns here, and what we can actually do is take all of these and rewrite them as a single equation, which is that the pressure at the start of the experiment multiplied by the volume at the start of the experiment divided by the temperature at the start of the experiment will equal the pressure at the end of the experiment multiplied by the volume at the end of the experiment divided by the temperature at the end of the experiment. And this is our gas law equation.